what I'm going to talk to you guys about today are the different kinds of flash. I think we like to call basically Flash 101. So if you take 10,000 steps back from what a flash array is all about, inside of it there's flash. Here we happen to use SSDs, but regardless of how you have it packaged, there really in the market are three kinds of flash that you'll find. And those three kinds of flash are SLC flash, eMLC flash or enterprise MLC flash, and MLC flash. And there's a lot of different properties about these flash, these different kinds of technology. But if you think about it from a really high level, as you go up this list, it gets more expensive. But as you go down this way, it gets worse for some definition of worse. So the first question is, well, what kind of flash do we use in the pure storage flash array? Well, it turns out we use the stuff at the bottom. And the reason why we do that, I think, is kind of obvious from this first arrow here. And that first arrow is expensive. So we want to take the cheapest flash that there is out there and make it viable for everybody in the market to use. But what about this other column? What about worse? Well, it behooves us to take a second to think about what's the difference between the three kinds of flash. And so they're all really made out of the same semiconductor process, and they have more or less the same cell design. The big difference between the MLC variants and SLC is in each individual cell, how many bits can you store? Up here in SLC land, you can store 1 bit per cell. Down here in eMLC land and MLC land, you can store 2 bits per cell. And there's flash that I'm not yet putting on the board, TLC, where you can store 3 bits per cell. And so, as you can imagine, that the MLC variant and the TLC variant is more dense. And because it's more dense, that's why you get more cost-effective behavior out of it. So in what way is it worse? Well, if you think about it, you have the same cell, and to store more data in one cell, you have tighter noise margins. That means that your write latencies tend to be a little bit worse on these MLC variants, and your program erase cycles, how many times you can read and how many times you can write to a cell and then erase it and rewrite to a cell, is a little bit worse down here than it is up here, because once again you have to write to a tighter noise margin. So in case that's something that you're not aware of in flash media is a lot like a CDRW drive that you might remember from the early 2000s or the late 90s. You can write to it multiple times, but once you write to it, you have to completely erase it in order to write to it again. And that's what I mean by program erase cycles, that as you do more program and more erasing, you introduce a little bit of noise into the process, and you have a tighter noise margin that you need to come down to. And so that's basically what I mean by worse on these axes. So then you can ask yourself, well, if this stuff down here is worse than this stuff up here, why would Pure decide to go use the stuff that's worse? Well, there's two basic reasons for that. So the first is just trends in time. So if you think about what's happening in time, and if this is our abstract quality metric here, and this is time down here, I don't know exactly what the curve is, but as newer generations of flash come out, they tend to go down in this abstract notion of quality. And so while today you might have, SLC over here, eMLC over here, and MLC over here, everything is sort of moving down this curve. And that's not going to change. That's a property of shrinking lithography. So we decided to embark on a design that really lets us use low quality flash. In fact, the MLC that we get today is probably higher quality than we'd like. We're probably paying for some quality that we're not using. when you look at other designs out in the market, and if they're using eMLC, and I don't think pretty much anyone these days is using SLC, but God forbid they are, what that's really telling you is that they looked at the other options to the right on this graph, they considered them, and they said, you know what, that doesn't work in our architecture. Well, to me, that raises some red flags, because tomorrow, when tomorrow's eMLC looks no different than today's MLC, what's going to happen in those architectures? What we've done is designed for flash that's way less reliable than even the flash you can get in the market today. So as things continue to move down this trend line, we'll be able to come right in there and pick up and use that new flash technology.
But that's just, the reliability is just one aspect of moving down that graph.
That's
if they may have looked at that graph and said, we need the performance of SLC for whatever reason. Is that possible?
That's right. So we're only talking about quality here, right? And so there's a bunch of other aspects you care about. What's the read bandwidth you get out of the SSD? What's the read latency you get out of the SSD? What is the write bandwidth, write latencies, etc.? And I think in all of these aspects, you really want to worry about what the difference between these guys are. So, you can solve a lot of your throughput problems by parallelism. And so then, if you're making your decisions here, it's probably around latency. And what we've found is that we can deliver consistent sub-millisecond latencies for user IOs by using the stuff down here at the bottom. And on the right side of things, we found that by building architecturally around throughput rather than latency and putting in some buffering right at the user layer, we can tolerate the additional write latencies that you tend to see as you go down the scale as compared to up the scale.
Are you using what, RAM for buffering?
We use a non-volatile RAM, and the technology there can change and mature over time. But the idea is to buffer and make sure it is persistent before we acknowledge a host. We don't have room for losing data, but that's the only bit of the system that needs to have good latency performance, and the rest of the system just needs to be able to keep up with that bandwidth, right? And if you think about it, as those cells get smaller, as we go from 19 nanometer to 1x to 1y in the fabrication technology, all of these other metrics also get worse. So your SLC or your eMLC, when you go to future generations of NAND technology, are going to have worse write performance, write latency, I should say. And so once again, if you look at a design that hasn't sort of thought about this from the beginning, that this is the trend of what's happening to the flash, you really ought to be worried about, well, what am I going to do when my write latency gets worse? Compared to a design where it's like, well, we wish it were worse now so we could get flash that's cheaper. And that's really the difference that you're looking at here. Now, one of the things that we haven't talked about is what's the difference between eMLC and MLC, right? And fundamentally, under the hood, it's actually the same silicon, right? The biggest thing that's different between these two things is the firmware and how much of the flash that's in the SSD that's really exposed. So, how many folks around the table know about over-provisioning? Excellent, everybody. But the basic idea, the basic difference between eMLC and MLC is how much extra flash do you have in there? How much over-provisioning do you have? Or how much flash do you have that's hidden that you don't get to use? And why would you have any flash that you don't get to use? It comes back to that sort of CDRW-like program erase properties, that you need to have some spare flash to write into as you're going and clearing out old data, and you're doing garbage collection to move data from one spot to another. And so the more spare flash you have, the faster you can do writes oftentimes, and also the longer your longevity on that flash is, because after all, you have more of it. Your writes are being distributed more broadly. And the hope also is that the more overwrites you can sustain before you have to do garbage collection and end up moving data and introducing what's called write amplification, writing the user's data more than once, and thereby eroding away some of the lifetime you have in your flash. So you can ask the same question we tried to ask a moment ago, which is, why on earth would Pure store MLC? Well, the reality of the situation is that the performance issues or the performance differences between these two can largely be mitigated if you stop treating your SSD like a hard disk. Right? It's a brand new technology, and this eMLC, what it's really trying to do is be able to slot in to a hard disk based application and give you the longevity that you expect and give you the write performance that you expect. Well, in the Pure Flash Array, we've started from the ground up designing a system for Flash. And so we actually have in our FlashCare technology algorithms that take this write amplification that we're talking about and drop it down considerably, basically to negligible levels. What that means is that you get greater reliability out of your flash without over-provisioning. Part of our ability to do that is by managing the flash holistically across all the SSDs in the system rather than looking SSD by SSD and trying to manage the space that's in them. So the Pure Storage Flash Array has system-wide garbage collection. And that system-wide garbage collection lets us keep to a minimum the write amplification, not on any given SSD, but also throughout the entire system. And we can make trade-offs at any given moment in time to manage the other aspect that we're talking about, which is performance. So we've built and designed the system to understand that every now and again, these SSDs, they're going to go out to lunch. And they're going to go out to lunch because they're dealing with the erasure process. And when they're doing that, we know that writes are slow to them, and we know that reads are slow to them. But what we can do, because we're cognizant of things at the entire system level, is just not do those reads and not do those writes to that drive and make up for it by writing elsewhere in the system and by relying on RAID, for example, to reconstruct the data that we can't read because the drive is being slow. And so we found that optimizing things at a system level really opens up entire avenues for what you can do with the cheapest flash out there, right? And as TLC enters wider scale production, you can be pretty confident that we here at Pure are going to look at the properties of that flash and ensure that we have a home in one of our storage shelves for TLC flash as well. Because after all, it's farther down on this expense curve, and what we're all about is figuring out how to give you enterprise level performance and reliability while keeping those costs to a minimum and delivering the most flash for the least price. Vaughn shows the slide of the responsiveness that you can get by in a hybrid versus a all-flash array. Well, we want to make sure more of your applications can go all-flash by making it more cost-effective. Joel, do you think I missed?
Sorry, how much of your advantages are going to come not just at this hardware tier, which obviously you guys are doing good engineering on that, and you're looking for that sort of sweet spot on the delivery. How much of it that's going to come on the software side, which differentiates you from other players in the all-flash space, or where do you see that way, and what's your real advantage? Is it going to be more at the controller side and the aggressive growth that you guys may make there on the software layers to get better dedupe and other features?
So that's a great question. So first of all, you can't get these hardware benefits without doing significant investment on the software side, right? It's all the work in the controller that carefully manages, that carefully does the translation from host reads and writes down to media reads and writes that enables us to use MLC flash today but yet deliver consistent sub-millisecond performance and to deliver flash longevity that it far exceeds even what the manufacturers rate their drives for. But going forward, data reduction technologies like deduplication and compression also help here, right? So the more you're able to reduce your data, the more you're able to, in particular, most of the workloads out there, after you do your initial data load, compression is the dominant factor. The more you're able to compress your data, the less you actually have to write to the media and the less you have to read off of the media. Well, what does that mean? That, you turn what would be large media I/O into small media I/O, and that just improves performance and it improves the longevity of the media. So I certainly think that it enables us to leverage the hardware, and it really will differentiate the flash array from the competing products in the space.
So you're a software engineer, right?
What's interesting,
I'm a software engineer that every once in a while dabbles.
and we used to always ask the classic questions, what's the MTBF, MTTF on this stuff, because no one trusted Flash. We've got a general acceptance of Flash, and it's a question not necessarily to you, but maybe go back to Vaughn and what we talked about earlier. Scott raised it. What's that sweet spot where people can get in at that early point? Like, I know a lot of us represent a lot of SMB spaces, and we talk about SMB, but when you guys talk about it, not you guys, but general enterprise vendors, when they talk about SMB, they really mean high M, not S, not low M. There's there's still a pretty steep entry point, although I definitely see what you're saying is that look at the bigger picture, longer term thing. Trevor Flash program, advantages in general against your competitors and in the marketplace in general, like because I can buy it, keep it. It's not like Obama where you can take a Flash and you can keep it. Period. Right? I can keep upgrading my controller and I've got renewed support. So where do you think that sweet spot is going to live for SMBs?
So today, there's some current technologies that we have and the density that's available. Price per gig, as Matt had shared, but
Right.
you're looking at an entry point that's going to be similar to that of a mid-tier storage array for one of the other vendors. And so what we see is there's times where some opportunities are too small for us to enter into. We compete with mid-tier, and you kind of knock the socks off that. But there's also a lot of times where we actually take out very large, monolithic, classic, traditional big iron arrays at a fraction of what the investment cost is. And so
yeah, and I mean, not to skirt your question, I mean, we definitely can't get under, like, let's say the $50,000 entry point bar with our products today, but we're well under 100,000, and so that tends to be, the very smallest enterprise arrays from EMC and NetApp can certainly get under that range, but most anybody that's buying a reasonable, tens of terabytes size device, you're in that zone.
I would also add one of the things that's very compelling in SMB that we see that Vaughn and Matt talked about a little bit is this ability to really consolidate workloads, right? And particularly things like VDI, things like databases, even in the mid-sized space, they're buying or dedicating storage resources to that workload. And so what you see is that in a lot of large mid-size companies in particular, they're spending more than they need to, and they're actually over provisioning storage to get that performance, or over segmenting storage to get that performance. And so you see organizations, I don't want to beat on Davenport, the county of Davenport, we got a bunch of mid-sized organizations like that have gone in because they have pain in one workload, and then go, wait a second, why am I running 5 arrays? Administratively, I used to run it because somebody paid for this one, somebody paid for this one, or I used to run it because VDI is stir-frying the array and I need to run my databases somewhere else. When you have a preponderance of performance, you don't have to do that.
The expansion on that is also how hard is it to run your array? And so with the flash array, you can basically put it into a closet and forget about it because the administration is so simple. And the administration is actually, in some sense, pushed up a tier. You create a giant LUN, expose it to VMware, and now you're just managing VMs. You're not even managing storage anymore. And so, simplicity here really does play a big role into it. You talked about mean time between failures on the SSD. Well, that's another important thing, that if you have an array and you have any sizable number of spinning disks, you have a part-time job of swapping out disks as they fail. And the reality is that even when we go down and use this consumer-grade flash, we don't see failures in the field. The flash simply does not fail if you take care of it. And we stand behind that in terms of just saying, well, if you have your array under maintenance, we're going to replace any media failures because we just don't expect to see them. right? That they're going to be that rare.
That was actually a contentious point in our first appearance on Tech Field Day. People couldn't believe that. And I think at that time we were saying we had seen absolutely no failures, and we promised to update folks when we saw them. Now, 4 years in, it's less than 5.
And I believe one of those 5 was really a firmware failure, right? So it's not the media itself that fails, it's the system, if you will, on that SSD, right? Which is, another reason, which is kind of counterintuitive, why going to MLC flash actually can help you build a more reliable product. This MLC flash, the media itself is shipping in your cell phones. That has to work, right? There's just too much volume for it to break. And the firmware that's out there is in all your laptops. And if that doesn't work, there's just too much overhead for the vendors that are selling you the laptops. So they get to a certain degree of reliability on there. And the volume is just that much lower on these products. And so you have, it's a general product architecture that we have. Code that's not executed probably doesn't work. Well, code that's executed, the corollary to that is the more it's executed, the more likely you are to get out the bugs. This has such high volume. It's a much better debugged product than the quote unquote enterprise grade stuff.
So you don't publish a duty cycle, so to speak? Somebody asked a question on Twitter about lifetime. So you've seen 5 failures of 5 individual drives or whatever you want to call them over 4 years.
Yep, exactly. And things like MTBF are challenging because we don't care about the pieces, we care about the whole system. And so from our point of view, we have an unconditional warranty. If you look at some of our competitors, they'll say, hey, the flash is warranted, but if you write it over a certain number of cycles, it's not, we won't replace it. Ours, if you ever happen to wear it out, which you won't, we will absolutely replace it.
Are some of those failures on smaller scale pure device deployments where they cannot, there's smaller amount of disks, and so that's constantly writing to?
I don't think there's any correlation back to the amount of write activity.
There's only 5 failures. There's no correlation. Unless you see it always from one model. Another question was about there's some discussion in the Twitter again about dedupe and whether that leads to hotspotting, and whether in fact I'm expecting that hotspotting is not an issue with SSD because the latency is so low that you just don't see that as being an issue if you've got hot blocks.
So it's a good point, and yes, from a latency perspective, that the read bandwidth that's available on each individual SSD is so high that we don't care about it. But it actually turns out that you do care about hotspots. And the reason you care about hotspots is because of reliability. And so you can actually, there's an effect called read disturb, where the fact that you read the media over and over and over again causes the values in the cell to wear out. And the firmware on the flash will fix that. But the way it fixes it is by rewriting the data. That's write amplification. That's reducing the overall lifetime of that device. We don't want that to happen. Once again, we do things at a system level, not at a individual SSD level. So we solve the problem using DRAM, right? That the total pool of dedupe data that's so hot that you're worried about it from the perspective of wearing out the flash media is small enough that we can cache it in DRAM. And so it's actually kind of a contentious point that when people ask us, do you have caches in your system, we'll frequently answer no, and then there's this little asterisk on the side. But we actually cache data not for performance reasons, but we cache data to protect our SSDs. It's part of flash care. It's part about treating this stuff really nicely.
So typically as solid-state drives start to fill up, there's a performance cliff.
Right.
How is that mitigated with Pure Storage?
So the performance cliff goes back to that discussion about over-provisioning. It's saying, and it's a write performance cliff, right? That the reads always perform just fine. But it's when I go to do a write, do I have a free block available? And if I don't, then I have to go find some data, compact it, do an erase cycle, and then write. And that's what really leads to your write cliff. So if you manage your flash properly so that you never try to write to it when you don't have free blocks, you avoid the problem altogether. And so remember, from the host writes perspective, that gets acknowledged when it's in NVRAM. So the management of this now turns from a latency problem, which is really where the write cliff shows up, into an aggregate bandwidth problem, where the bandwidth is across all the SSDs, not an individual SSD. So if a single SSD happens to experience a write cliff problem for a short amount of time, no big deal. We actually don't want that to happen because it's hard to predict, and you holistically want to be able to write to all of your SSDs. So if you manage the amount of free space they have, for example, by trimming space off the SSD, you can avoid ever getting into these pathological situations.
As the array fills up, like your entry one here, I'm looking at your specs. And as it fills up, would we expect to see the CPU usage increase as it's trying to compress more or find better ways to compress while IO's coming inbound?
So we manage capacity globally, and so we have spare capacity on the array to sync writes. And so we expect you to be able to fill the array up to 100% and maintain performance and keep that performance. Now, your specific question was about CPU utilization. As a software guy, I get annoyed whenever I see our array not pegging every CPU at 100% all the time, whether it's brand new or whether it's old. And that's because there's always useful work we can be doing. Right? Some of it is opportunistic, some of it's sort of scrubbing data to find, are there any latent errors in the system? Some of it's pushing data into deeper compression, what have you. There's stuff that can be done. So we've designed our software to constantly be trading off between one activity versus the other based on what's most important. So from a CPU specific point of view, no, I mean, if we've done things correctly, that should be pegged at 100% the entire time you own the array.
Do you guys find because you're obviously all flash here, is there a reason to want to still front load stuff closer to the hypervisor? So is the flash read cache kind of mentality going to still be strong, and do you promote that? Whereas you've got most of the real good stuff happening simply in the storage tier. Like, do you find that that's going to be somewhere we can still get further advantages, and do you recommend that?
I mean, it's really about how sensitive are you to latency, right? If you need 100 microsecond, 200 microsecond latencies, you're not going to get that from the flash array, right? You're going to have to put some host-based solution. But bigger picture, we think most of the applications that we've seen don't need that level of performance, right? That really the big quantum leap here is going from disk level millisecond, multi-millisecond performance to sub-millisecond performance. And the problem is that once you put in some storage in your hosts, you open up the whole, set of problems of how do you back it up? What do you do when that server fails? You lose a lot of the benefits of consolidated storage. And so I would say to the extent possible, no, we don't see that.
Yeah, I would add, the construct of direct attached storage, if you're measuring bus speed versus network latency speed, you're measuring in the range of, microseconds. Those microseconds get blown up, and that argument no longer bears weight the minute that you don't have a cache hit. And now you're going to disk, because now you're getting into the tens of milliseconds. And again, this is where we look at things like Little's Law and say your transaction has a number of I/O requests in it, and you're bound to the slowest transaction or the slowest response to the I/O request. In addition to that, a lot of the direct attached storage designs don't mean that you will service or receive your I/O requests from a local resource, right? You don't have to have as many hosts with storage as you have hosts that can read from it. So now you're still going across the network. And so that construct, I think, in the shared scale-out architecture of like data closer to the CPU is faster, it really gets negated out of real world. Not that there isn't a benefit for it. I think the new tier 0, as Neil said, is in memory computing. If you need something that's that sensitive to latency, it's in memory.
Is that, how much has been derived from like the ZFS model for this? Because it looks pretty familiar to me.
The underlying architecture is inspired by a lot of the file system work that was done. So log structuring, for example, to avoid overwrites. ZFS does it, and we're also doing it. Nothing specifically looking at what did ZFS do, but similar sort of academic lineage, if you will, back to the idea of how do you build something that really can deal with the fact that you don't want to overwrite in place.
Can I ask a question about the upgrades? I actually have a question from a contact who's a customer about one of the branch upgrades that required some guest VM traffic to be shut down. I don't really understand the full background to it, but he just asked me to ask you guys about it. That it turned out not to be non-disruptive in this instance. 3.2 to 3.3, I think, was the upgrade. So if you could provide some info, that would be great.
I'd have to look at the specific case for why that is. whatever the situation being, we'd consider it a bug. So if we're not able to non-disruptively upgrade, we'll fix it. There was an older upgrade where we had an issue, for example, with Windows hosts. We identified it, we warned all of our customers about it, we found a window where we could upgrade them, and we learned from our mistakes, and we no longer have that problem. 3.2 to 3.3 I find surprising, but I'm not going to say that it's not the case. We have a great support team, and I'm sure if that's what they told him, there's a specific situation there. But just know that internally that is a bug, and we will make sure that it gets fixed.
Yeah. So it's a one-off, really. It's
I don't want to dismiss it as a one-off. There's a situation clearly that this customer faced, but within engineering, we don't look at these things and say, oh, well, that's that customer's problem, that's not our problem. We look at it and saying, what can we do more holistically to make sure that the product actually functions in all environments. And I was speaking with somebody over the weekend who I know personally, who happens to also be a customer, and he mentioned, he was like, oh, well, we had this problem, but don't worry about it, that was our fault. And my feedback to him was, stop thinking about it that way. There's nothing that you can do that's your fault. That's just something more proactive that we need to do on our support side to make sure that even if you're making mistakes, we're the ones identifying it and pointing it out to you. And that's the general support philosophy we have, that we want to make sure that the array works in your environment full stop. And anything short of that, we're going to prioritize in fixing.
Where do you find that the workloads are inappropriate? And where would you maybe say, like, maybe this isn't the right array for you? I mean, obviously, you're never going to say, oh, don't use this when you use somebody else's stuff. But, you know,
we actually have said exactly that.
Is there a workload?
I mean, I don't remember the customers, but if you're taking compressed video and doing sequential streaming, I'm pretty sure somebody will at some point in the conversation say, can I find you a nice, competitive array to use, because this probably isn't the one for you.
Yeah, pre-compressed things. Hadoop's an interesting one, right? Workload that's very serial, designed for cheap disk, distributed in masses, not so useful or accelerated with flash.
Yeah, any of the object storage stuff, obviously, it's just meant to be JBOD, cheap disk. It's not really designed for it. So that's another one. On the OpenStack side, I guess, I know you guys do have a Cinder driver, and do you get a lot of folks that are kind of requesting on that side of the space, or do you find it's mostly the VMware and Citrix side, because you guys are obviously strong in the VDI space?
We're definitely seeing increased OpenStack interest. So it started out with service providers. We're seeing, large enterprises start to get there. It's tire kicking in labs and experimentation right now more than full deployment, but there's enough interest that we've upticked the priority, and definitely are engineering towards keeping ourselves recent in OpenStack.
And what's the current driver that you guys have support? Is it only sort of like Havana release on the Cinder side, or where did you guys come into the OpenStack space?
We have a driver today supports Folsom.
You guys go all the way back, okay.
We have Folsom introducing support for the new features provided to the Cinder driver with Havana in the first half of this year.
Okay.